So what is actually going on is, again, similar to what we are discussing in the first section. There are this tensoring technique can be used to prove some other result by playing the game slightly differently. And I want to sketch in these problems how to, and let you do the details, how to do Borel-Weil theorem, the Borel-Weil-Bott theorem, which gives the cohomology H E X O lambda for all rays lambda. So this is basically what we are going to use to prove the statements about global segment. So the question is, what if we go to other chambers? And the answer to this question is given by this theorem of Borel-Weil-Bott. Actually, it's a Bott's addition to Borel-Weil, which after Rochek, I will discuss this moment. What happens if you go to other chambers and take away there, then you can sort of take a while group orbit, sort of reflect these along the walls, and you get over here, and then you connect this with lambda, and the current number of walls you cross. And the cohomology in that degree is non-zero. All the others vanish, and the cohomology in that degree is, again, finite dimensional representation with lowest weight lambda. So this is, I will state precise statement, and basically the idea of this exercise is to prove this. So let's look first at a two situation. Where, so if X in this case is one-dimensional projective space, and in this case, we know what happens just using elementary algebraic geometry. Let me also mention here that, because this is very important, that O lambda, as we discussed last time, is a d L minus rho module. I mean, this is just the issue with our labeling, but this implies that cohomology of O lambda in general nonsense. I mean, if we calculate cohomology, we can calculate cohomology, say, by injecting resolutions using d lambda minus r modules, and then this will give us the cohomology modules, all the global sections of these guys. But because there is a natural homomorphism from the end-of algebra into global section of d lambda minus rho, then these guys are always u theta. And of course, again, some elementary result from algebraic geometry says that they're all finite dimensional. So we know that the modules in Borel-Weil-Bott are just finite dimensional u theta modules. Therefore, if theta, okay, I should be more precise. Theta is the orbit of this d lambda minus rho, and we know that I mean, definitely, if I have two, say O lambda prime, then they can have their cohomology will be u theta module. So if theta and theta prime are different orbits, then those representations have to be different. So, in particular, and this is part of the exercises, if you think about this lambda in Borel-Weil is an anti-dominant weight. So in Borel-Weil situation, you subtract minus rho, so which is inside the negative chamber. So when you shift by lambdas, you get something which is in a shifted column here, so definitely regular. So lambda minus rho must be regular for any say lambda, which gives us a finite dimensional representation by Borel-Weil. Therefore, the first observation is that there are no finite dimensional representations which correspond to singular fundaments. So then minus square is in the wall. And this implies that none of those is a u theta module for a singular orbit theta.
So singular is just not regular.
Yes, yes. So this is when lambda minus rho is in one of the walls of in the H star. So if lambda minus rho is there, corresponding O lambda cannot have any cohomology. All the cohomologies have to vanish because there would be finite dimensional representations of u theta. So there will be sums of irreducible representations of u theta, but there are none of those, just by the highest weight. I mean, there are more geometric ways of proving this, but I just want to show you that this follows by analyzing the action for u theta. So, for example, another exercise related to this is, which follows from the formulas we proved in the first collection. If you look in this case, these line bundles just their sheets O n, and so we have O n and one, and say to O. I mean, this corresponds to negative change over remember it, because of our choice of ordering. There is the corresponding weights, minus and so on. And then I have O zero, these are regular functions, and then O minus one, and then O minus two. And this is the line bundle which corresponds to vanishing of all cohomologies. And if you look at the seriality, this is the exercise, then you see that in pairs, symmetric points, I mean, this action of the Casimir tells us that symmetric points with respect to O minus have the same infinitesimal character. U of G acts by the same U theta. Infinitesimal character is standard term for the actual center of the envelope. So, I mean, we know by Borel-Weil here we have finite dimensional representations, and here we have no cohomology at all, and here, I mean, you have by say there, you know, the global sections vanish, and first cohomology has the same dimension as the corresponding point here. I mean, looking at the global sections, and the infinitesimal character of those representations is the same. So if you look at the list of representations, you realize that if you look at this point, the line bundle corresponding to parameter with symmetric with respect to -1, you will get the global sections vanish, and first cohomology is an irreducible finite dimensional representation. Should have here symmetric finite global sections, and this is exactly the statement of Borel-Weil-Bott in this case. So you can see it using these results about cohomology and UN, and this remark about action U theta. Now, so this is the first problem, is to sort out this by comparing the action of the Casimir. The second one is to prove this different. And then we are going to discuss how to prove this in general. Any questions about this? No. Oh, okay. So now the second approach to this problem is by using the same trick we used in the first lecture and the second. But now we are looking at this point. So we take O minus 1, and then I will take this O module and tensor it with some finite dimensional representation again. And this is, of course, the same as O minus 1 tensor over OX then script Vn should just is for now we can again filter this sheet by, I mean, here, remember what we did, we look at the point and back, look at the stabilizer, which was just a Borel, and then on the end, this Borel, there is corresponding flag. And the filtration given by this flag gives us a filtration of Vn, which corresponds to all the weights. Start from -10, go to n, and now, I mean, in our calculation, n is the highest weight. So we get a bunch of a graded object consists of a bunch of line bundles, which should just correspond to the weights -n to n, and they jump by 2. And then we have the corresponding, then we tensor with total -1, we have a shift by 1. And now we, again, so the exercise is to look at the eigenvalues of the Casimir, these things, and then you see if I look at say what I get here, the extremal weights. So what I will get line bundles by a shift from -1 to this phase. And if I do the calculation, then I get that if you think about this, I will have the composition of this tensor product with respect to the action of Casimir, and if I look at the component corresponding to time state, say here, so I will get -1 plus n. This will correspond to a sub in this filtration, and here I will have -1 minus n, which will correspond to, I think I mix this up.
I think the positive one's supposed to be the quotient.
I mean, I missed this up because my the parameter actually corresponding to the line bundle different in certain sign of this. So I want this would be correspond to this would, you're right, this is correspond to the closure. And what do I want? This is plus. And the exercise is that from this orbital pole that gamma x of n is equal to h1 x of O minus n minus 2, because this is the symmetric point with respect to -1. And this is exactly what follows from zero duality, and gamma x of this guy is equal to 0. And we know that h1 here is here, and n is negative. Positive. And this is exactly Borel-Weil-Bott. And the reason for this is the following, that if we look at this short exact sequence corresponding to our eigenvalue of the passenger, so this is the calculation, the exercise, it gives, because of the symmetry of the eigenvalues of the passenger, the eigenvalue of this guy, or corresponding to the highest possible eigenvalue of the passenger, has length 2, corresponds to 2 points just symmetric with respect to -1. One of them is, so it is the sum. So this is this right here is this sum, and this guy is the quotient as the Borel-Weil-Bott. Cohomology of this guy is just that is in the cohomology of -1. So we see that this sum has no global section from moment that's from long, and this guy is the quotient. So the connected homomorphism gives us the isomorphism of the global sections and this -2, which is the statement of Borel-Weil-Bott in this case. Great.
Okay, just in that picture, what are the upper indices in the two pictures?
In this,
No, the one below.
the one below, I mean, I messed this up. I mean, I just, so the observation is that these guys have the same infinitesimal character. So if I look the extreme one, it corresponds to extreme one over here. And if I do this correctly, the labels are correct, then I get that 1 over there is this guy, and 1 over here is this guy.
So that piece, so you get a rank 2 bundle.
Yeah.
The filtration with those 2 pieces. Okay.
Those 2 pieces, and the homomorphic is 0 in all degrees, because we took something without homology and tensor with the vector bundles, some of this, so this is and then we see that homomorphism just is a statement of. So this is the naive exercise. So now the third step is the same idea in general, but done in higher rank. And I will just do picture argument for SL3. And I mean, the general argument requires a bit of work. And so this is my anti-dominant chamber. And for example, let's take a line bundle corresponding to weight, singular weight in this wall. This guy has no homology. And now we tensor it with a finite dimensional representation for us, so that say the highest weight is here. Try to find 10 different color. So I'm tensoring with finite dimensional representation. This weight. So what I will get here, I will get to the weight here, and then I'm shifted. So this is a lambda on the left. And this side, let's assume that this root is alpha. So this is lambda plus S alpha nu, and then I have the other weights. So I get some pattern like this. And then what do? We play the same game. I mean, these 2 points or these 2 points and the same value for it. But you see, one is on one side in one chamber, the other one is in the other chamber. So this tensoring argument is usually called tensoring across the wall, because, as Jordan pointed out, if now I take an eigenspace, let's assume I take an eigenspace corresponding to this action of this center, then the action here and here on the corresponding line on this integrated object are the same. They will be the same eigenspace. So you will get a vector particle which has is filtered, and the graded object consists of 2 homogeneous line bundles corresponding to lambdas on different sides of the wall. And then you look at long exact sequence of homology in this equation, and what do you observe? That, say, for example, if this guy, if you take a picture of this guy, let's have global sections, and it will be a quotient, because this corresponds to I state, so this is the one corresponds to sun. So the global sections of this guy, the star, will vanish, because the global section of the tensor product vanishes, this one that is in the wall, and the connecting homomorphism will identify global sections here with first homology. And then I mean, I just use a picture to illustrate this. If you play with the argument, that you will see that you can apply this to the same any oval to just answer this finite dimensional representation. And the message always will be that crossing one wall will move cohomology up by one. So this is the observation. So, and this is actually the statement of Borel-Weil-Bott theorem in general. So let me just formulate this. First of all, I have to define the notion of the length of the element of value. So, first of all, I think value W, it's generated by reflections with respect to the roots. So our positive root systems in Laplace that defines a basis of the root system by such that sigma plus are just sums of roots from pi. And if the corresponding simple reflections with respect to simple roots, then any element of the value is a product of simple reflections. And if P, the number of simple reflections is minimal for some W, this is called the reduced expression of W, and this P is called the length. So any element in the value is its length. And another interesting exercise is to show that if I take, say, a chamber corresponding to some element, a chamber, and I take, say, a negative chamber, I take lambda, and then I take its conjugate over here, that will be lambda. Then the length of this W is the number of walls you cross if you go from lambda to W1.
You might need to wiggle that.
Oh, excuse me?
Oh, no, sorry.
Yeah, so I mean, this is just to, so that you don't have to write this reduced expression. Look at this picture, so this is my antidominant, so here I will use simple reflections, here I will have two reflections. Yeah. Okay, so now I can give you the precise statement of, oh yeah, now of course you can say, but I related, say, the cohomology for this parameter to cohomology for this parameter. What about the other? If you use the same tricks as in Borel-Weil-Bott, proof of Borel-Weil by shifted by this tensor, you can show that cohomology, if at one point here you have say P cohomology, then in all the others you will also have P. Just do the shifting inside the chamber and you know the result will be the same, except that the parameters will change. So in this way, if you look at my localization notes, then the logical argument is kind of different. First, I show that cohomologies create the same in all the chambers, and then you actually play this across the wall argument to find out what is the cohomology of the line bundles. And so the final theorem you should get is the following. So if I take lambda in H star, so first of all, there are two options. First, if lambda minus rho is singular, then H star of the homology of X O lambda is 0. So for all these. So this is just an infinitesimal parametric statement. And the second statement is if lambda minus rho is regular, then of course I have an element which is inside one of the chambers, and then there is this mu which is antidominant, and W in while loop which is unique, such that lambda minus rho is equal to W. So this is, I mean, lambda minus rho is conjugate to this mu. And then if I look at homology,
Sorry, Dragan, I actually can't see what you've written there.
let's see, let me define another pen. Right. So this is lambda minus rho, which is regular, is conjugate to an antidominant mu in the negative chamber, and because of regularities, this W is mu. And so what can we say about the homology? That so HP of X O lambda is equal to 0 if P is different than length of W and H length of W of X O lambda is equal to F with lower straight mu. Again, if you assume that lambda is anti-dominant, then I mean W is equal to 1, and you recover the same for L.
I'll put a question about part one.
Yeah.
So it seems like from part one, like as soon as you're singular, all of your cohomology dies. So it's not like cohomology is picking up how many of these, like to what extent you are.
Exactly. Yeah.
Maybe one way to think about it is that you, from D1B, you have a lot of different maps to D1Ps. And if you're kind of O of -1 along any of these, then you already die by pushing forward to one of these. Yeah, thank you.
I mean, now, when we were discussing this, let me point out that one thing follows from this picture, that in any chamber, you can realize finite dimensional representations as homology of some line one. So one who does what is the generalization of this statement. And the generalization is that if you look at the corresponding derived categories of the lambda modules and the theta modules, then they're equivalent. And the equivalence is given by derived functor of cohomology, and the quasi-inverse is derived localization in the regular case. So basically, one finite dimensional representation has several reincarnations in the various chambers, but they live in different degrees. Unfortunately, or fortunately, depends what is your interest. If you generalize this from Bailing-Son time, then if you take a representation and localize in a chamber which is not anti-dominant, you can get you can get D modules is various. I mean, you can get a non-trivial complex with non-trivial cohomology in different degrees. So basically, if say you study T structures in perversions for these various chambers, the localization of the standard T structures and modules in each chamber gives us a different weird T structure in the modules. Not related, and there are so-called intertwining functors, which we are going to discuss, which relate the pictures in different chambers. And if you think about if you go from the right category to one chamber to global sections and then localize in a different chamber, then you will get the functor from D modules in one chamber to D modules in the other chamber. But one can describe this functor geometrically. Intertwining functors of Bayes and Bernstein, and this allows you to use this strategy that you can prove theorems by choosing your chamber when you localize, or then you do some particular property, and then you go back. And so you will see how this works later. But this is the indication that there is some rich geometric from Borel-Weil-Bott, rich geometric formation in these different localizations corresponding to the different chains. This is one remark, and then the last exercise, which is related to what I just said, if you use this across the wall trick for arbitrary beyond modules, which integral with respect to some simple root alpha, then you observe that from long exact sequence, then the analog of this tensor product, the cohomology does not vanish. You don't know anything about it. But you get the long exact sequence. On one side, this long exact sequence that's called, I mean, the cohomology exists in degrees, say up to n. When you cross the wall, you can get only something in 1 degree high that follows from long exact sequence. So another exercise is to show that as you cross an integral wall from anti-dominant chamber, cohomology can grow at most by 1. And this, for example, for generic lambda, there is never cohomology. And this is also an important remark. Okay, so I spent more on this than I thought. I will write you the synopsis. I mean, basically, this is just playing wild groups and these. Any questions?
Just so I understand the exercise, in part 1, we are just tensoring OX with Vn, and we get that filtration you described where there's only one of these slime bundles of the Whereas in part 2, if we shift everything over by -1, then like half of them are submodules, sub-bundles.
Yeah, if you look at the graded objects, so you can organize them in pairs. Like here in this situation, these are these shifted lambdas which are symmetric with respect to the small, and here are points symmetric with respect to -1, and they correspond to the same action of the center. Same generalized eigenspace.
The pairs do.
Yeah. Yeah.
And so the exercise is to show that.
Yeah, I mean, here one has to be careful because it's possible that you need a power of maximal ideal the center to kill this, but so you have like some Jordan form type arguments, not in the Borel-Weil thing, the action of the center was semi-simple but graded thing. Okay, so any questions about this? So what is the time situation?
Well, we can have a break now, maybe.
Okay, so this is exactly what my question, because I want to start talking about cohomology. I mean, we are going to need Borel-Weil-Bott to find the cohomology of d lambda. And another thing I want to point out is if you think I'm not cheating, everything I used here was not, there is a connection between U theta and D1 minus rho. I used just the trivial thing that this guy maps in the global sections, not that this is a mess of because I just used linear algebra for the action of the center.
Oh, okay, so to do this exercise, you can't assume the full localization.
Yeah, I didn't use localization theorem at all. I just used the action of the center and these decomposition. I mean, eigensheet decompositions under the action of the center.
And the vanishing statements, which we've already proved last time.
Yeah,
But in the anti-dominant.
I mean, in Borel-Weil-Bott, in Borel-Weil, we didn't use this. Yeah. So basically, this was not used, and then we are free to use Borel-Weil-Bott to prove the cohomology of the lambda is what it is, that higher cohomologies vanish and global sections equal to U theta.
But I think I don't think that
So,
but I guess you can answer the
to a
theorem. So regular
generated by the longest and so
you're see, those naturally one of the changes
Yeah.
So like you've sort of got two like we haven't had election going on. The
like that's kind of object the like
objects that you really care about, you want to naturally like I just
I mean, if you say state great variable, but there is there this is too wrong. This is why it's trying to so, and if you and the negative change
and then if we want
say
to okay, what
the bundles by positive change and they're and this just forces
I'm a week I've been doing that for the last 10 days. So that's all it was.
just in the instance again, trivial structure.
It's also been fun. I've been thinking a lot more about that.
Associated. So
very fun.
of course that one to me is
What are you applying for?
because it has
Essentially to compute arbitrary.
yeah, I mean,
Which I think I can do now. Like I have an outline of nice year to be concrete and a year to implement. And then and then there's
going
I did this project we did.
representation
Did you see the you seen the plot and stuff?
No idea. I just talked about it. Yeah, I should check.
No, It's like a.
And to relate it by these are those who have again twisting the economic complex. So it's this is the reason why it's wrong. Because going in the 16 of differential operator, if you want to consider it as so the opens it's again going to be what differential because that might certainly yes, this is like what you really do. So this is something built in.
Yeah, yeah.
Yeah, for some of it.
Yes.
And then finally, it takes one.
Anything that
I think it's actually does. Yeah, because I was like, I think this is why in this picture there's no wall and
just on the weekends.
we do that at the back. Oh, it's just the term.
But now it's just.
So what I want to do is today is construct these business sheets and so let's by x as before the quadrant. G and UG is then belonging up here. And then observe that G acts, the group acts on X, and then by differentiation, we get an action of B, but via tangent vector fields on X. This is B of tangent X for this. And let's deal with this now without. Then how extends to the homomorphism of UG into just global ordinary differential. Now the denoted by U naught OX concerned with over C U of G. So this is like sheet 5 and all the algebra. And this has a structure of a sheet of algebras, and there, well, this is a short exercise. That if I have F tensor with C, and C is in the algebra of a G times G, so eta F and G regular functions, right? Eta is an element of this enveloping algebra. This is equal to F times tau of C G tensor eta plus B times A. So since these guys generate U naught, one can check that this formula defines the structure of associative algebras. And you're going to inside this, we can also look at G naught, which is a simplified B algebra. And it defines that it's a sheet of B algebras when the commutator is defined when using this multiplication using J. This is equal F tau C G, and so eta minus G eta F, and so and plus and B.
So should that be a G naught? Up there?
Or G naught, yes. Thank you. If you look at how can be extended to a map OX from G in the sheaf of tangent vector fields. And if you think what this, then I can define B naught, which appeared before, is the kernel of the map tau from extended to G naught into tau X. Remember, B naught was equal sections of a vector bundle which is over X cross G over X. And then over each point X, we take here a subbundle which consists here, I think, corresponding. This was the convolution of the bundle or else. And by this construction, this naught is can be also described as a kernel of this. File. So now, if you think about this, the group G acts on B naught, and if we differentiate this action, then B naught is preserved. So from this, it follows that elements of B naught commute with the elements of Lie algebra G. And since this is the kernel of this action now, you can see that also they do not do anything from the action functions use them. So from this, you can show that B naught is achieved of ideals in G naught. The sheet of three elements. This is just to check this directly. And then you can form U naught and generate B naught, U naught, with an ideal partly corresponds to naught. And if you think about this, you see that it's nothing else than ordinary differential operator. So this is just the construction of differential operators in this setting. And what we are going to do, we are going to modify this construction a little bit to get all the ones. And the idea is to first replace B naught by N naught, where N naught is the, again, we have been before this is sections.
So, Dragan,
Yeah.
I'm a little bit confused about why B naught is a sheaf of. Well, I'm a little bit confused about just G naught. How should I think about that? Like, why is B naught an ideal in?
Because I mean, you have to do some calculation to do this. And so this is saying in my notes. And I mean, the main trick is that if you write down what's going on, these at each point C is given by the differential operator at the point it this element doesn't move the point, so that you let's see how to explain this. I mean, another way of arguing this, that if you check that this is of Lie algebras, this is of Lie algebras, and you just take the current, this is really formal. But that the main problem is to figure out how to check all of these formal properties of these things, which I have in my notes, but since I spent so much time discussing exercises, I thought of skipping, but I can. If you want, I can go through this.
Well, I think I'm just like maybe just what are the stalks of B naught? Like because like G naught is just
I mean the geometric fibers are just Borels.
And so then wouldn't we get a sheaf of Lie algebras as the quotient? Right, like if we have a sheaf of ideals inside, with like an ideal inside a Lie algebra, and then the quotient should be a Lie algebra. Oh, sorry, it's a sheaf of its ideals as an OX module, not as a Lie algebra. Like it's not a Lie algebra.
Is it as an OX module, but also it's a parallel homomorphisms of two sheets of B.
Okay.
So it is.
But then isn't the image going to have fibers of size G mod B and will be a Lie algebra? So what? Yeah, I guess what is that like? What is that bundle of Lie algebras?
It's just, I mean, sections of Borels with this weird operation.
Maybe I'll bug you about it.
The fibers are of dimension B, not G1.
The fibers of B naught.
Yeah, exactly.
Yeah, I guess I'm just like G is a sort of, I don't know, simple Lie algebra, and we've got the sheaf of ideals which only exists because we're on the flag variety. It's like we can't say we have a sheaf of ideals in any point sense. So I guess I'm just like, I don't know, wondering what, like what quotient Lie algebra. I think I'm just unfamiliar and confused.
No, I mean, this is completely formal construction.
Yeah.
So, I mean, the way you check these formulas is that you use this. So this is no X module. And then you define differential homomorphism when the commutators without a sufficient many elements of points vanish. And then you show that C gives you the differential homomorphism for F. So these guys map into differential homomorphism for this, and this can extend as a map of U naught into differential homomorphism. So this, and using this remark, you can check that since by looking at the action of element 1,1, we can show that this gives you an associative operation. And then you look at this as fitting inside there, and you look at this multiplication into this structure of the algebra. And then you define B naught as a kernel of this. I mean, look at, there are more details in my notes, and we can discuss. I mean, this is something you just have to calculate in your office and without distractions to the words. And then, I mean, this is, you just take the potent radicals instead of not. And you look at the quotient of U naught and and we call this BH. I mean, let me just, I didn't ask your question, but let me just jump ahead a bit, because I think you'll see that this is less severe than it looks. Now, remember, and this is why this H is here, that H naught is B naught mod N naught. So this was trivial OX module for X in its global sections where this Dragan algebra H. If I look, this tells me first that if I look at the global section of X, H, we get a natural map of U of G there, because this comes from here. And also, we get natural map of U of H, because H naught sits inside here, so that, and we have this situation. On the other hand, I can look at the center of the envelope algebra. Okay, so which sits inside the G. And also I have Chandra and this is the one without Rocher. There is this map of the center in the page. Let me point out that since the group has on the page and the action induced on H naught is trivial, so this means that sections, I mean elements of your page map in here in the center of global sections. So this is another thing to check. Therefore, we get, I mean, this you can check this diagram. I just want to explain construction, maybe next time I speak, I can fill in details because I don't want to stop in some unnatural spot. So this maps into gamma X H. So I probably should explain more details. These things related to critical expressions. So I get this homomorphism. And then we have a Theorem, which is critical for this, is that U of G, this map tensor from C of G, U of H into gamma X is isomorphous. And the second statement is that the global section of this DH higher moment. So this is actually the critical result one has to prove. now, let me point out how this implies the theorem. First of all, if I take lambda in H star, then we define this lambda defines the homomorphism of U of H in the complex universe. So we define that the lambda is D of H tensor over D of G with D lambda plus rho. Lambda plus rho defines a representation of H, therefore a homomorphism of U of H to C, and we can tensor U of H over U of H this representation, and then this is the definition. And now, if you think about this, so again, I have to make more details. So here we posted out Borel. So locally, I mean, if I use the fact that on the group I can write locally an open neighborhood of a point, this is corresponding Borel times the opposite nilpotent radical, and this implies the statement. This is the shape of the radical operator. Here, I just do this twist, which locally can be trivialized, but globally of course not. So this gives me a sheaf of twisted differential operators. This is one remark. The other remark is that I can do a free resolution of d lambda minus rho possible by H modules. And then if I tensor this, then I get the product of this tensor this by, and I get a bunch of copies. So this is free resolution by D of H modules of so I tensor by this guy. And now, since we know that the cohomology of elements of the previous resolution type of homology vanishes by the statement 2, so this implies that higher cohomologies will be bounded. So this is the reduction of this. No, I'm sorry. H. I mean, through this, wouldn't really allow us to go. Greater than 0. Yeah, we get the mobile sections of this, just this thing over there, answer. So I'm answering U of G by Z of G acting on C lambda, and this tells me the global sections of lambda are equal to theta. So this theorem immediately implies the statement for the lambda.
So you have -4 minutes.
Oh, sorry.
No worries.
Okay, so let me just say a word. Sorry for that. Over time. Here, my D of H was defined by quotienting by the U of naught times n naught. So you can look at n naught and construct a Cazul complex corresponding to this n naught. So the complex, I just want to explain the strategy. So this will be U naught tensor over OX dash and naught it will resolve the array. Great. I mean, this is my complex. This is exterior algebra and not a bunch of say vector bundles, tensor not and the of H. And what can write down? I think this is just again the idea which comes from the algebra, algebras, just a sheetified version standard complex. And one can show that this is our resolution. But it has to do with the algebra. And then this one needs the cohomology of these guys to show the statement about UH. And this is what we discussed before using Borel-Weil-Bott. One can show that if you look at P to F, the cohomology appears just in degree P. And you can calculate this module. And then from this, and from one gets information.